Groups are very fundamental in maths, and at the core of a lot of interesting questions. What do we mean when we talk about them? I plan for this to be the first in a series investigating groups, eventually leading to Galois theory, probably one of the most surprising applications of group theory. For today, we'll try and get an intuitive understanding of what a group is, and look at an example. We won't worry about formally defining a group just yet. So what exactly is a group? We can think of groups as the mathematical objects that describe symmetries. So now let's talk about what we mean by mathematical objects and what exactly makes something a symmetry. Defining what mathematical objects are in general is too big a question for this video. You'll have met many before. Let's look at the first mathematical objects you're introduced to. What are they? The counting numbers. Think about what links these pictures. That's right, the number 2. The number 2 encapsulates that idea, the property of two-ness. Thinking about the counting numbers in a mathematical sense, we don't use units such as rocks, sheep, or score marks on a page. This means we can work with a much larger range of numbers. We'd be hard-pressed to consider a million of anything without some sort of abstraction. As mathematical objects, we can study the counting numbers, for example how they interact with each other through operations like addition, subtraction, or multiplication. As part of this abstraction process, we introduce concise notation that allows us to work efficiently. For example, we write numbers using base 10, and computers use binary. This idea of abstracting is what groups do for symmetries, and we'll discuss those next. So what are symmetries? Let's look at some geometric symmetries, and see if we can spot what the underlying idea is. You've probably seen lines of symmetry before, or reflection, perhaps rotational symmetry, maybe even shift symmetry. Here we're shifting an infinitely long line. What is it that makes these transformations symmetries? Well, the shapes look the same after we performed them. In fact, if you close your eyes while we did them, you couldn't have told they happened. Symmetries arise when we have invariance, i.e. something that doesn't change. Invariance is a very important idea, at the core of a lot of key maths concepts. I should add that if we want to keep track of what these transformations do, it's common to number the object. Here, we've numbered the corners of the square, but could have just as easily numbered the edges. The key idea is that if we remove the numbers, the object looks the same after forming the symmetry transform. So to recap, symmetries arise when we have invariance. So, combining, we see that a group is a mathematical object that describes symmetries, how they behave, interact, and so on. Let's take a look at one of these groups. We'll look at the group of symmetries of a square, which is sometimes known as D4. D4 consists of reflections and rotations. Let's look at a picture of all the 8 things we can do. On the left-hand side, we see we have 4 reflections, and on the right-hand side there's 3 rotations and 1 more, doing nothing. Doing nothing is a symmetry because the object remains unchanged, invariant. So to collect these into a group, let's put them into a set. A set is just a collection of things, and we denote it with curly brackets. We often call this do-nothing symmetry the identity, and it's usually written first in a group, so let's rearrange. We mentioned before that mathematical objects use concise notation, and drawing each symmetry out is certainly not concise. So let's try again. This time, we'll give each symmetry a name. However, this is still quite a lot of effort to write out, and we can't easily see how they interact with each other. But we can be more efficient. Let's shorten the names. Using more mathematical notation, doing nothing, or the identity symmetry, is usually written ID or id. In that same idea, let's call a 90-degree clockwise rotation R. Then we see that all the rotations are just repeatedly doing r, once, twice, or 3 times. So we'll denote this by raising r to the second and third power. Since we can't get it via rotations, let's call a horizontal reflection f. So now let's stop introducing letters for a moment and see what happens if we do f followed by r. To keep track of what happens, let's number the square. And do f. Then do r. See, this does the exact same thing as a reflection through a diagonal. So why not just call that diagonal symmetry FR, since they're equal? This saves introducing a new letter, and we start to see how elements interact, although we won't fully explore that today. In fact, it turns out we only need letters for 2 symmetries to write out the whole group. This notation is much more concise. This is very similar to how you might see D4 written in a textbook. But in a textbook there'll be one small difference. In group theory, when we apply symmetries, we reverse the order that we write them. So let's fix that. So now doing F then R is written RF. This can seem quite confusing, but we have a good reason to write them like this. Finally, if you look at D4, you might also see this quite strange looking notation. We'll discuss this next video. But why do we have these different ways to write the same thing? Well, why do we use base 10, score marks, or binary notation for the numbers? We choose the notation that suits our purpose. Notably, when using RF notation, we can ignore the underlying object, which is in this case a square, just as we see with the counting numbers, which ignore any sense of a real-world unit. So we see that as mathematical objects, groups are to symmetry, while the counting numbers are to tallies or score marks. They abstract and allow us to investigate the concept of symmetry much more deeply. Anyways, thank you for making it this far. That's the end of part 1, but the beginning of our exploration of group theory. Next video, we'll see that symmetry doesn't only appear in shapes, and decode that strange notation we saw before.